In the concluding video for this week's lecture, we'll take a look at NoSQL. We briefly talked about it when we discussed about Hadoop, HBase being one of the NoSQL databases that was very popular. Aadhaar runs on HBase as an example. So in today's video, we'll actually dive a little deeper into what NoSQL comprises of. So like I mentioned at that time, NoSQL came to be known as NoSQL really, but then over a period of time, it started to absorb the world of SQL as well, meaning the syntax associated with SQL became something that many NoSQL databases also wanted to adopt, given its popularity. So nowadays, if you ask me, NoSQL really needs to be expanded as not only SQL. Okay, so why NoSQL at all in the first place? So we spoke about CRUD as one of the critical operation types, right, when it comes to OLTP systems. So NoSQL became like a very viable backend for OLTP workloads to counter the entire, proprietary nature of databases that was popular at that time. But not only that, it became necessary to start to optimize the backend and the CRUD operations to suit specific structures in which data was naturally present. So what are those structures? The first was what's called as key value. Second was what's called as column oriented. Third came to be categorized as document based, and fourth was graph based. Graph meaning relations based. So the other characteristic of NoSQL databases was the fact that they always seem to have this trade-off that gets provided between consistency, availability, and what's called as partition tolerance. So what does partition tolerance refer to? It refers to the fact that if I have my NoSQL system spread across multiple machines in a cluster, and for some reason the cluster loses the information about who my different machines are, right? Then in which case it has what's called as a split brain problem, whereby some machines do not know about the existence of other machines. This could happen for various reasons. One reason could be there's a network failure that prevents some set of machines from communicating to other set of machines, but then they can communicate with each other. In which case, everybody in this set thinks that all the machines in this set are dead, and vice versa. And in which case, can they continue to service new workloads? Excuse me. Sorry. Can they continue to service new workloads, or do they just catastrophically come to a halt, saying that, look, I don't have those other friend machines anymore, so I can't service any new workloads. So that's what's called as partition tolerance. Availability, obviously, we know that already. Consistency, we know that already. So this trade-off between consistency, availability, and partition tolerance, it's abbreviated to at times be referred to as the CAP theorem. CAP is the acronym for consistency, availability, and partition P. So it's called as a CAP theorem, but then in reality, it's actually not really a theorem as much as it's a trade-off. It's a proper trade-off, right? The trade-off comes from the fact that you can optimize to do two of the three things, but you cannot get ever all the three things in one go, which means you cannot get 100% partition tolerance, 100% availability, 100% consistency in one NoSQL system, because you have to, by design, optimize for two of the three only. That's the that's the CAP theorem. That's what the researcher who came up with it analyzed the NoSQL systems and said, okay, yeah, these distributed systems have to have this problem to be satisfied. So yeah, almost all these NoSQL databases allow your configuration settings to tweak a couple of these parameters, but almost all of them have chosen to, in practice, uh, provide 100% partition tolerance, because that's the part that's very hard to reason about for an average developer. Right? That's a very complex problem to manage. So this part is usually not configurable. Consistency and availability is where you can play along with. So when you say when I say play around with consistency, I mean if I make a change in one um, NoSQL system, um, basically it makes a change in the primary copy. Within how much time does it make the change available in a replica copy? And if the time is instantaneous, then it means the next read that happens, right, will be able to read whatever is being written just the previous second or previous millisecond, right? That's what I mean by that's what it refers to as 100% consistent. On the flip side, opposite end of the spectrum, if I make a change now, if the replica gets to see that eventually, what does eventually mean? Like some unknown period in time in the future. It could be within 1 minute, it could be like 15 minutes, it could be 1 hour, it could be 3 days. That's what's called as eventually consistent, right? So there's a big spectrum of options that are available. Notice that in the world of databases, by that I mean relational databases, this problem does not even arise, right? In fact, the asset semantics that databases have is natively guaranteed by the database using this concept of a transaction. So the C in asset is actually consistency, right? So the notion of a transaction, where you begin a transaction, then you prepare a transaction, then you commit a transaction. It's called the two-phase commit of a transaction. That natively guarantees asset semantics, which means it natively guarantees consistency and availability. But the world of databases does not really have a design consideration for partition tolerance, because it's not designed to be that kind of a distributed system at large scale. Whereas NoSQL is, so therefore it needs to think about these kinds of things. Okay, so NoSQL, like I said, became really popular because firstly it was much cheaper than the proprietary systems that existed out there, but cheaper for a problem statement which is very high scale. And the way it dealt with that high scale, high performance need was by using a distributed parallel architecture that leveraged commodity hardware, right? So, meaning there was nothing that was shared across the machines, no sharing of memory or CPU or disk or anything like that. Every single machine had all the resources required for running it, like CPU, memory, disk, network, all within itself. Likewise, I could just string a bunch of these machines together, and this kind of an architecture is called a shared nothing architecture. Nothing is shared between the machines. And parallel scaling, meaning I will just spin these up in parallel, and voila, I have 10 times the capacity, 10 times the bandwidth, 10 times the speed. So that was the beauty of the NoSQL database, and they've really delivered on that promise, right? And so much so today, I don't think you can think about any single system which is run by any of these famous B2C companies like Myntra, Swiggy, etc., which does not use a NoSQL database. All right. One of the things that NoSQL databases are in general not really good at, compared to, let's say, the RDBMSs of the world or the OLAP systems of the world, is if you have to read a set of data. Notice that I had said earlier on that the NoSQL systems were optimized for CRUD operations of single records. So if you go back to the customer master example, so I am IRCTC, I have my customer master, I've got my payments data. I want to come back and update the phone number for the customer, because the payment information, as part of collecting that, I've got the new phone number to which the OTP verification is happened. In that setup, I can come back and update that particular customer's phone number in a jiffy using an update operation, which is one of the CRUD operations that the NoSQL supports, because I'm operating on one record. But for some reason, let's say that I have to go back and update every single customer in ISATC today to say that the person is not a loyal customer. Why? Because I'm launching a new discount program only for loyal customers, and I want to get customers to sign up afresh. In which case, all the existing customers on my books are all to be treated as customers who have not signed up. And for some reason, I decide that let me go and update, let me add a new column. The new column says loyal customer, yes or no. I go update that column to have the value no for all my tens of crores of customers. That's a very, very, very bad idea in NoSQL. Why? Because it's not optimized for CRUD on a set of data. Forget about CRUD, right? Just reading that set of data itself is going to be a challenge, relatively speaking, of course. Okay, let's dive deeper into the types of NoSQL. How does it trade off? What are they good at? And this is something that we should all know. So the first NoSQL data type, database type, is key value. Key value store. By the way, the conventional parlance, you could refer to these technologies as NoSQL databases or NoSQL stores or just a store, right? So in some cases people refer to this as key value store. So really what they mean is key value NoSQL database. Okay, the key value store is the most simple and efficient. Why? Because all it's doing is just storing a value for a key. In general, the value is actually just not a singleton value. It could be like an array of values. The key is a critical element. The key becomes the index on which the entire table or the data set is indexed on. So think of it as like a gigantic hash table, right? The hash table does the same thing. We spoke about how a hash join gets planned and we hash it to a key, and the key is like looked up in a table. That's exactly key value, right? So think of this as a glorified hash map. Right? So the hash table structure is used in this kind of a setup. Why? Because the asymptotic complexity of computing a hash function is constant. Right? So to figure out where to insert a key is actually a constant time operation, and that is a critical element of the performance that the key value stores provide. Now, the key value stores all actually take these values that are existing and store it along with the key, meaning the key and the value go hand in hand, so that when I do the hash lookup, I can immediately get the value as the array of values, right? So this kind of a setup is what's called as a row major format. Row major format because all the key and the value pairs are occurring together, and the next key value pair, the next key value pair, and so on. This kind of a setup is actually there in all relational databases by default. So all of the different columns come together for a row, and then the next row begins, whose entire set of columns are stored together, and then the next row, and so on. So when you look at the actual file that gets created by the RDBMS in the backend, when you open up the file, assuming you're able to read it, because usually it's byte encoded, let's assume you're able to read it, you'll see the entire row being stored, and then the next row, and the next row, and so on and so forth. Likewise, the key value store is also like that, because the hash table, the point of the hash table is actually look up the value very quickly. So the value gets stored in line along with the key. Okay, so what are the examples here? One of the most common and super popular open source key value stores is Redis. In fact, Redis is very, very popular as a cache, and we'll talk about the architectural patterns in the end. But yeah, as a cache for a classical RDBMS. So Redis becomes very useful for that. Aerospike, super popular again. It's touted to be one of the fastest general purpose key values NoSQL databases. BerkeleyDB, I've mentioned this briefly before. It's like a poor man's database, very lightweight. You can just embed that within a program that you ship along with your code, and you can actually access data as though it was stored in the database. DynamoDB is one of the more really well-researched pieces of NoSQL databases that's part of AWS. Google has something similar. Um, uh, anyway, so a lot of different options. And this is not an exhaustive list, by the way, right? A lot of options. Okay, the next type of NoSQL database is like a column-oriented store. So here, it's not key value anymore. It's actually a bunch of values. The bunch of values all have their own descriptor. Descriptor meaning a column name, right? So in this, basically, the columns of those values that are of the same context. Context meaning they potentially come from the same domain or they come from the same source. So in which case they're all organized together as column families. And then those column families are stored together, but multiple different column families are stored separately. So let's take an example. Again, customer master IRCTC. So one set of column family, rather one column family of columns could be related to demographics. Meaning, what is the age, what is the date of birth, what is the gender, right? So those are classically asked always by any booking. So I collected information, I put it under demog column family, and within the demog column family, these three things come together, right? So the column name would be gender, value would be male, column name would be date of birth and something, and then column name would be age and something, right? So that's demog. You could have another set of column family, another column family of columns, which is related to preferences, right? The preferences could be upper birth, lower birth, middle birth, or could be like the credit card type of payment instrument that you use. So that's actually stored in a separate column family. Still indexed by the same user ID, by the way, right? So now, if you look at the underlying store, the underlying file system where the NoSQL database is storing its data, you would potentially find that all of the column families are actually separated out based on the key. Meaning, for me, my column family of demog and my key get stored together. The next entry you will find in that file potentially would be your key and your demog column family. Whereas my preferences column family and my payment column family could be in completely two different files. And in that same file, your preferences column family and your payment column family will be present. Right? So the column families are spread out, but the set of columns belonging to a column family are stored together, and the same column family across multiple different keys are stored together. So in this kind of a setup, we call the storage as a column-oriented storage or column-oriented store. Why? Because you could actually look up a specific column much faster than if you were to look it up from a key value store or from an RDBMS, because you're avoiding the need to even read from the disk these other column families which are not stored together. So think of it, right? There's a demog column family file, there is a payment column family file, there is a preferences column family file, and right now for my initial login or for some kind of an analysis, I really want only some kind of an analytics to be computed based on demog, right? The entire table size is, let's say, a terabyte. Because these three column families are equally important, let's assume it's 30%, 30%, 30%, right? 1/3 distribution in terms of data volume. But because I want only the demog for my analysis, I can get away with reading only 333 GB of data from disk. So remaining 667, I don't even need to read from this. Forget about filtering after reading, right? So dramatic improvements in terms of performance if you need only certain columns. Okay, so that's the advantage of column oriented. In fact, ever since column oriented databases became popular, NoSQL databases became popular, the relational database guys have also caught up. So now some of the RDBMS technologies also provide column oriented data storage. Works in the same kind of a concept, right? Anyway, column oriented stores, they are typically using a hash table structure, but then the value that gets stored is basically the column family itself, and the column family has multiple columns, right? and then those columns themselves are stored in a row-oriented manner within the column family. Now, in this kind of a setup, if you want to add a new column, super easy, right? Because anyway, new column families are completely different files, right? Behind the scenes. So if you want to add a new column, you just create a new column family and you add your columns there. You're done. It doesn't touch any of the existing data sets, right? So the cost of operation is like almost constant. The aggregation queries, if you make it specific, if you project out only certain columns that you're interested in aggregating, then again this can be done really much faster than if you were to go and do it in RDBMS or key value store. Okay, yeah. But the flip side to all of this is you have to manage multiple different column families. You have to manage the structures associated with it. What if there are changes within the column family? That becomes much harder to think about. One of the worst operations to do here is an operation that touches all the column families. In which case, you're now having to take all of these different column family files, join them, and that join itself was not required, right, in a key value store or a row-oriented store. Whereas in a column-oriented store, join is actually the first operation. So, like ad hoc complex SQL queries to read a set of data together, those are not very good to execute on these kinds of systems. So, examples of technologies here, HBase is one of the first databases that took up this kind of a design. Cassandra was actually very heavily inspired by HBase, but then Cassandra's creators thought that HBase has some very critical architectural problems that they went about solving, but they retained the goodness of HBase. Google Cloud Bigtable is actually going to be one of the technologies that you might be using in this course. It's actually built heavily, rather motivated heavily from HBase, but yeah, it's got a similar column-oriented architecture. Okay, the third category of NoSQL databases is what's called as a document store. The notion of a document store, don't get too hassled by it. It's a very simple model of operation. Instead of treating every data as a record, which is what a RDBMS or a matrix style relational database would do, in a document store, every record is a document. So what's the difference between a document and a record? A record has like a connotation of a very well defined structure, whereas a document is fundamentally open structure. It's not unstructured; it's still structured. It's got actually a set of key value pairs, but it's open structure, meaning it doesn't prescribe that these are exactly the only keys that I support, right? Or these are exactly the only types of values that I can put in for these keys. That's on there, right? So it's open structure, meaning you can keep adding new key values, not a problem. But those key value pairs, they all come together under the context of a particular document, and the way the document is identified is using what's called as a document ID, right? So the analogy is just like you have a table of rows or table of records, here you'll have a collection of documents, right? The collection is like the same thing as a table. So a set of documents is called a collection. So the document store is it's highly flexible. It doesn't actually impose anything, like I said, as in terms of modeling constraints like a column family store does, or column oriented store does, or a key value store does. It's actually a generalization of the key value concept, right? So it's highly flexible. While it actually also has a very specific patterns of workloads that it can optimize for more powerfully than the simple key value pair kind of store, right? So for instance, in a key value store, because it's inline, it's a row-oriented store, the only index that you need is key. You cannot really index on the value. Whereas here, because there are multiple key value pairs for every single document ID potentially, it allows you to create indices on every single one of those, or a select group of some of those. So that's up to you, right? The second thing it does is, if you need the ability to do like free-form natural language search, like Google search, on some of those keys, basically, like some of the values of those keys, you can do that, right? And that's like a very specialized workload only for those column types. So that's possible. Typical document structure itself is actually JSON based. So don't think about document as like a Word document or a text file or something like that. It's a JSON document, and JSON is how you interact with it in terms of placing data, retrieving data, and storing the data as well in the backend. Two of the most absolutely popular examples of technologies here are Mongo and Elastic. In fact, Elastic is so popular that you could actually think about Elastic as its own category. Meaning, if you want to build a search engine and you couldn't afford Google, the Google Enterprise Search, then and you don't want to pay money for Amazon's Enterprise Search or Microsoft's Enterprise Search, whatever. You could actually construct your own open source search for your documents using Elasticsearch. And Elasticsearch is highly optimized for that model of free form search over all the values that are part of the document. You don't need to do anything special, right? Just index it, store the data, and then you're good to go from then on. And in fact, Elastic also has like a very good set of technologies in the front end, which allows you to visualize the search and do some very interesting reporting analytics on top of it. MongoDB, likewise, it's a very common OLTP system, OLTP backend document stored. The flexibility MongoDB provides is unchallenged by any other database. You can keep adding new key value pairs to your documents as your data model evolves. Nothing needs to change about your backend database. So that kind of a flexibility is immense. Okay, so the last of the categories here in NoSQL is NoSQL stores. So these are highly optimized for storing data along with its individual relationships. The key word here is individual. I'm not talking about set-wise relationships like primary key, foreign key, not that, but individual relationships. Like for instance, my record is connected to my credit card, which is connected to my household, right? So that relationship between these three data elements is comprised of it's actually very specific to me, and that kind of a relationship it might not be common to many people at all, right? Like for instance, many people might not even have a credit card. They might not even have a concept of a household that's registered within the IRCTC system. So that's very powerful, right? If you're able to capture relationships at that individual level. To do that, you have to really think about data elements as nodes, vertices, and edges. Sorry, there's a typo here. Edges are as specific relationships that connect them. So the edges can have properties which say that when did this relationship form. Likewise, even the nodes can have properties, and those properties can be used for adding more context and info. So the reason why this kind of a structure is very useful is certain kinds of operations become super easy to do with it, right? Like for instance, what the problem of graph traversal or relationship finding is an operation that is a common operation in certain industry types, like for instance social network, like for instance recommendation engines, right? In those kinds of setups, the ability for you to look at relationships and use that as a way to look at data that are connected to each other is a critical prerequisite. You can achieve the same thing using SQL, by the way, on RDBMS, but it will be way more expensive compared to doing that on a graph store. So, for instance, if you ask a question for all of, like for a customer A, let's say me, right? Give me my friends. So in a RDBMS, you have to go do index lookups and then filter and then come back and do a list. In a graph store, I would just get the entire operation done in constant time because I just need to know which nodes are connected to me where the relationship is friend. That's it. So super fast. One of the most absolutely popular examples here is Neo4j. Again, open source. In fact, almost all the NoSQL databases that I mentioned here, except for those from the public cloud, are open source databases, Apache licenses. So you can definitely just download and start playing with it yourself. So Neo4j is very good. Amazon Neptune itself is actually a Neo4j clone, is what the industry insiders believe, with some modifications, so that's okay. ArangoDB, another example of a NoSQL database which supports like a graph-based storage. Alright, so last slide here. What are the common architectural patterns? The reason this slide is important, firstly, is that there are so many NoSQL options, and you can think about a specific need you might have for your application, and you would end up having like 2 or 3 NoSQL options to choose from, which are very good at solving for that need. So that's the kind of proliferation of technologies that's happened here in this space. That's actually good, right? In my view, it's really good that we have so much choice. Obviously, it means that as a designer, you have to be careful about exercising the choice. So some common best practices is what I've documented here. So each NoSQL actually ends up having its own syntax. So even though you might have 2 or 3 NoSQLs to choose from to get your job done for your specific application, because the NoSQL variant or NoSQL interfaces are wildly different, right? Each NoSQL has a completely different kind of syntax from the other, but your application need is the same, right? So the common architectural pattern is always think in terms of APIs. So you define the APIs as part of your application. You say, what do I need to emit out? What do I need to receive back? Right? And those standard APIs, in turn, implement the respective adapters for the NoSQL system that you end up using behind the scenes, such that at a later point in time, if you find that, yeah, I made the choice in NoSQL, that's not good, let me go back and choose another option. I can just change the backend, change the API adapters, but I don't need to change the application front end. Right? I don't need to change the application logic. That separation of concerns is crucial. Otherwise, you're going to get hit with every single time the NoSQL changes. Now, the other reason why this is important is some of the NoSQL systems, because of the proliferation, have died death over a period of time, because they've stopped becoming popular, they've stopped having open source contributions, etc. The other reason could be because they're so popular, they might have so many different versions keep coming up, right, on a regular basis. So that could also be a challenge, because you always have to test for backwards compatibility. So for all those reasons, separate out your application from the database using APIs. Okay, so one of the other common patterns that you'll see is that some data sets are always getting accessed, even within the NoSQL database. So we spoke about NoSQL being conducive for very high frequency, high concurrency, low latency kind of operations. Even within that, you'll find that some data sets are getting accessed again and again, disproportionately more frequently than the other. So like the 80-20 rule, right? In that kind of a setup, one of the common architectural patterns is actually to use caching. The reason being, the cache is even more closer to the functional logic which needs that data, and it's optimized to use memory, right? Redis is a good example. In fact, Redis as a cache in front of any other NoSQL system, in front of any RDBMS, is a very common architectural pattern that you see in the wild. So think about caching actively. The third thing that you see in the real world with most B2C workloads is that they need instantaneous access to the data. So think about IRCTC or Myntra, Flipkart, Swiggy. You need instantaneous access to your data as a customer master data, irrespective of where you log in. Right? I could be logging in from Chennai, you could be logging in from Calcutta, or I myself could be traveling to Bombay and logging in from there. I need access to my data set instantaneously. So a common architectural pattern that gets followed is NoSQL system is a distributed system, right? It's got multiple machines working with it. Even despite that, it might still have latency problems if you access your data from somewhere else, or somebody else accesses their data from somewhere else, etc. So one of the common techniques that gets used is what's called as sharding. And that too sharding, which is aware of the geo latencies, right? Like accessing from certain parts of India could be slightly more slower. Like for instance, the Northeast, right? Could be slightly more slower because it has to travel over the multiple routers to come to the central network and so on. I'm talking milliseconds, right? I'm not talking like obviously minutes, but even that could be like disruptive for certain kinds of applications like payments. So sharding is a very good approach. In sharding, what you do is you figure out the way to partition your keys such that the partition is geo-aware and is making keys which are more likely to be accessible within the geo available locally within the geo. So, as an example, let's take that IICTC northeast to south north example, right? So, for the most part, I'm south based, right? For the most part, you might be east based as an example. Somebody else might be northeast based. In which case, it makes most sense for the practical way to implement this to be that there is a NoSQL system which is in south, which has only the south region resident data, right? And that data set is actually there. The east region has its own NoSQL system, same NoSQL system, same technology. Northeast has its own NoSQL system, and that northeast NoSQL system is maybe housed in like a central region within the northeast, like let's say for instance, like Shillong, right, or Itanagar as an example. And the east region is housed in Calcutta, right, or Bhubaneswar. South region is housed in Chennai or Bangalore. The technology is the same, right? The data is actually partitioned across these three regions. That is a very simple way to achieve sharding, which is geolocation aware. The last of the common things that you might see in the world in practice with B2C workloads is that they always have to be available, right? If you log into IICTC today, you don't expect to see a message that says come back later. Maybe once, okay, twice, thrice, you start to complain to the Indian Railways Minister on Twitter, right? So how do you get this always on availability? You need to have replicas of the data. And those replicas have to be spread across multiple geographic locations so that even if like something catastrophic were to happen in one location, you still have access to that same data without loss. And those replicas have to be kept in sync with consistency. What kind of consistency are we talking about? Eventual or immediate? Like those are, things that you have to think about carefully. Great. So with that, we have concluded this week's lectures. We started off looking at SQL, mainly from an OLAP perspective. And then we looked at various cost-based optimization options available to you. We looked at your best friends when you go down that road, which is explain and analyze, and the reason why those two things are very important. How do you reason about different types of joins? How does the optimizer reason about it? And explain gives you that window into the minds of the inner workings of the Spark SQL. We looked at Spark SQL's syntax a bit as well. We also looked at UDFs as a way for you to extend your own coding in case the declarative is not flexible enough, but you're trading off the fact that the optimizer cannot understand what you wrote anymore, right? Because it's not a native function. And with that, we stopped with the SQL side on OLAP. We came back and looked at a very important topic on the OLTP side, which is NoSQL databases, looked at the different versions and different types, what type you want to use for which kind of scenario. And the common pattern, doesn't matter what type you use, but there are some common patterns and how do you optimize for them. Thank you. With that, we close this week's lectures.